Before we talk about your grant, I want to introduce myself. My name is Dr. Hamza Anwar of Cure Brain Cancer Foundation. I'm based in Sydney, Australia. I'm honored to award you a continuation grant of $70,400 US for your project on targeting MYC
Thank you very
expression
much.
and copper chelation to treat DIPG. And I want to pass it
Thank
on
you
to
very.
Leslie, who has a few words.
Hi, Dr. Kazoli. On behalf of the collaborative, we are so excited to get to help continue your research and to be part of this great research that you're doing. It's really exciting, and we're excited to get to support you as a collaborative. I am with Anna's Bake Sale Foundation. We are an organization that started when my daughter, Isabella, was diagnosed with neuroblastoma. And we have started this foundation and have been connected to Cure Starts Now and have since become members of the collaborative and are just really excited to be part of all of this research that's going to such a good cause and very near and dear to our hearts. So we thank you for what you're doing, and we appreciate everything that you do to help continue the research. And I'm going to pass it now to Tamara, and she's going to share her story.
Hi, Dr. Kazoli. My name is Tamara Ikis. I am a president of the Reflections of Grace Foundation, and we have been with the DIPG DMG collaborative since it was formed. So we were one of the founding members. So we are so very proud to be passing this grant to you across the world. We are sitting here with, this brings 4 countries together, and we really feel very strongly that our togetherness so much greater if we are funding people throughout the whole entire world. And that is something that, our foundation and the DIPG DMG collaborative has been so proud of doing. So we are thrilled that you're here today, and we're thrilled to award this grant to you.
Thank you, Tamara. So I also wanted to add, Ricardo, that so CBCF, so Cure Brain Cancer Foundation, we've been supporting the collaborative for almost a decade now, and seeing some of the work that you guys have been doing is truly inspiring, truly amazing. And so I just wanted to ask a quick question. So this project is a continuation of your last grant. Can you talk about what you discovered and where you want to go next from here?
Absolutely. Thank you very much for the support so far, and thank you for the next step. So basically, my project is the concept is about deliver drug or RNA therapy directly to the brain. And there are 2 major limitations in doing so. The first one is the brain is protected by a blood-brain barrier. And so usually most of the drug, they are, even if they are working in the lab environment, then when we go test in vivo, in animal model or clinical trial, they often fail because of this filter, that it's a protection for the brain, basically. And there is another problem, another issue. Lipid nanoparticles that are used recently for delivering RNA therapy or novel drugs, they actually are mainly collected by the liver. And they are collected by the liver because the body feels that this structure is something that it needs to be detoxified. So the liver function is to clean the blood from everything that is not normally doing his job there. So from this, we created this concept to create a new delivery system that could overcome these 2 problems, looking exactly like something that is already present in the blood. And what is the most abundant things in the blood is red blood cell. And we use the red blood cell, load them with our therapeutics, and then we transform them into little vesicles that are actually the delivery system. And when I applied for the first time, we were on the first preliminary testing in vitro. We progressed through the in vitro testing. So the technology, we set it up all the variable and parameter to produce this structure. And I'm actually very happy to say that we had a good result to transfer a marker into the DIPG cell. This has been done in vitro, and now we are starting to test in an animal model. We also have achieved the preliminary data in animal model. So far, it's about biodistribution. So before going to therapeutic, we want to be sure that this structure is able to cross the blood-brain barrier and doesn't accumulate into the liver. practically the second part of the project that I applied this year, it will focus completely on the animal part of the development. So far, we can say, okay, we are able to transfer the material, the drug from the vesicle into the target cell. But of course, passing from a little plate in a lab to a complex structure that you inject and it can go everywhere, filtered by liver, spleen, kidney, that's a bigger and more complex situation. So far, what we observed, we marked this structure with a fluorescent molecule, so we can track where the molecules are going. And we observed from the preliminary data that we are running right now that they are able, we see the signal in the brain. So we are already very, very happy for this result. And we don't see, compare side by side with living nanoparticle, we don't see a bigger increase of signal in the liver. So the next step will be, of course, repeat the experiment, have more data, be more robust. And when everything is set up as concentration, loading capacity and everything, we will run a real therapeutic assay. And the final idea as the grant, we want to use two different hit. One on a gene that it's MYC, that it's a gene that regulates the metabolism tumor. So tumor are crazy cells that are always wanted to grow. And this is the key point for the proliferation, but is also somehow the weakness, because they need a lot of energy. They need much more energy than anything else in the body. And we want to use this pathway basically to be very focusing on the tumor, hit the tumor metabolism, and be more safe on the healthy cell. Healthy cells can absorb the heat much better than the tumor because they don't need to have so fast metabolism. And on the other hand, we want to bring a drug that wasn't able to reach the brain. We tested this copper chelation therapy in my lab with my collaborator Orazio Vittorio. He's decade that is working on copper chelator. He saw a good cooperation between the copper chelator and the target I'm hitting. In this way, we want to bring the drug inside as a proof of concept, because once we bring one, it gives the idea that whatever we load, we can take it there. And then we can also continue to explore different combination and maybe use your network to find the better composition of drug and RNA therapy. But what we want to really achieve in this next part of the grant is a proof of concept. So basically show that I can bring the drug there. The technology is able to attack principally, mainly the tumor cell. And I have actually a very low level of immune response. So if we achieve these three parameters, then we can also start to trigger and try different combination therapy with maybe other collaborator and find the perfect cure that eventually we can bring in a clinical trial.